So just a little bit of review here. Obviously, we're talking about intra and intermolecular forces. Remember, intra holds one molecule together. Inter holds many molecules together. And that's kind of the next three forces that we're talking about here from yesterday. We'll add on to that one as well. The first one, remember, was dipole-dipole. This is just for a polar molecule. Could be any polar molecule for the most part. Just a basic dipole-dipole, so a little bit of negative end attracted to the little bit of a positive end on a different molecule, right? Okay. So if we have these two here and these two here, that has to be in between them, yes. Okay, that's the attractive force there. And of course, that's intermolecular forces. We talked a little bit about hydrogen bonding yesterday. Hydrogen bonding is just a specific type of dipole-dipole. It's for a specific set of polar molecules. It has to be, remember, what were the letters that we have to talk about here? That's actually up there, but what's the specialty here? What's the special letters that we need to look at? Yeah. Bonded to, perfect. So H bonded to NO or F, yes. Somewhere in the molecule, anywhere, okay? As long as there's an H bonded to an, well, I'm gonna tell you right now, if it's HF, as we know, they're bonded to each other, yes? Because that's all they can do. But it's H to O somewhere in the molecule, okay? Or H to N somewhere in the molecule. Those are hydrogen bonding molecules, okay? Basically how this works, of course, is again, we have a very electronegative atom. We have lone pairs on that electronegative atom, pulls electrons towards it, okay? Leaves hydrogen as a bare positive nucleus. So remember, we get the very, very positive end. We get a very, very negative end. And that very, very negative end is attracted to another very, very positive end. Again, it's between molecules. So if you had like HF and HF, it has to be that in between there. Okay, it's a ramped up version of dipole-dipole. It is special enough to have its own category. I'll prove that to you coming up here. Okay. So far we've looked at two polar types of molecules, two polar cases, I guess. What about nonpolar? Do nonpolar have some kind of force that holds them together? And well, of course, if you haven't picked up on this, probably. But you know, even if we just look, the example they give us here is look at FF. Okay, is that okay if I just do that just for simplicity's sake? Is there a force between nonpolar molecules? Do you agree that fluorine FF is nonpolar? Yes. 4.0, 4.0 balances out, right? And FF here, right? And we'd be talking about that there, yeah, that bond in between. Is there something that exists between these two nonpolar molecules? And, well, let's take a look at Cl to Cl, okay? What's the next one here? BR. I don't know about you guys, but I'm kind of getting a little bit cold. Brr, 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 brr. No way. Brr, brr. You can smile, it's okay. All right. That quiz was not that bad, was it? No. All right, and aye, Captain, my captain. Aye. All right. So look, these are all nonpolar, right? Obviously, I hope we know that. We have some, yes, we have some review to do. Hey, I've marked your tests. I will give them back to you tomorrow with this one here. We have a lot of stuff to go over. But I thought I'd wait till you did this one, and hopefully they kind of even out a bit, if you know what I'm saying. Not saying that all the marks are bad. Just, yeah, not as good. But listen, these are all nonpolar molecules. You know, they have the same electronegativity, they have the same pull on the electrons in the middle and stuff like that. But you know, notice here, like this is a gas, right? So what does that tell you? Let's just talk about this for a second. Hopefully, I kind of picked up on this from yesterday. But what does that tell you about this bond in between here? Strong, weak? Yep. It's probably fairly weak, right? They don't hold on to each other very well, do they? If it's a gas, that means they're independent of one another, kind of thing, right? They're just floating around. And this is a gas as well. Okay. So again, this bond is probably not that strong, right? But these are two nonpolars. So is this one. But now all of a sudden, this one's a liquid. So now this tells you what? This here, that interaction there, whatever that is a little bit stronger, yes? Because now it's a liquid. And we know intermolecular forces, hopefully from yesterday, is all about states, right? How well they stick together. And this one is so good, it's a solid. So obviously, look, if there was no such thing as a force that holds these together, they'd all be gases, right? There'd be no way for them to stick together. But obviously something's happening here because we have different states for all these these are nonpolar molecules. I picked these ones because they're easy, right? We could do the same thing with CF4, which was that on your quiz today? CF4 or CH4? I don't remember. CF4, I think. You know, that's a nonpolar molecule. We could talk about the same stuff with that, you know, and so on and so on. But yeah, I mean, I guess we'll see, right? I don't remember. Every class is getting a different one, so I don't know which one you guys had today or not. But same thing. It's nonpolar. Those are nonpolar molecules as well. So we could talk about the same thing. So what's happening here? Well, obviously there has to be some kind of force. Why would we talk about nonpolar, all this stuff, and then be like, oh, there's no force? Like, that doesn't make sense. So yeah, something's obviously going on here, right? Gases have little interaction between molecules. Liquids have a little bit more. There's a little bit more attraction. And the solids are locked in together, right? So there has to be something going on there. So here we go. I'm going to let you copy here, but let's just take, let's just stop here for one quick second. It says here, the attractive force that acts between nonpolar molecules is called the dispersion force or London force, or sometimes actually called van der Waals forces, okay? But we call it the dispersion force. We'll call it London forces, okay? They act between all molecules, but in nonpolar molecules, they only are the only force that are acting on molecules, okay? And we're going to stop right there for a second. Here's the important part of this, and this is really important for us. It says this is the attractive force that acts between nonpolar molecules, and it's called London forces. Dispersion forces or London forces act between all molecules, okay? All molecules. Put your phones away. All molecules. But in nonpolar molecules, they're the only force, okay? So what they're saying is London forces act on all molecules. They act in dipole-dipole molecules. They act in hydrogen bonding molecules as well. So London force is a part of every molecule, and once we kind of talk about what that London force is, you'll kind of understand why this is a factor, okay? So London forces are in every molecule. So every molecule that you drew here today for your quiz has London forces as part of it, okay? London forces are in all molecules. However, okay, if it was nonpolar, you'd say London forces because that's the only force. But for example, if it was a polar molecule, you'd pick probably between dipole-dipole and hydrogen bonding, okay? But we'll talk about that tomorrow probably, okay? Now, here's what London forces basically is. It's quite lengthy, okay? And we will talk about this, but it is quite lengthy, but that's basically what's happening here, okay? And then we're almost done here, so. And there's a couple key words we have to remember here. Absolutely, very important. Nonpolar molecules can form temporary dipoles. So let's make sure we know that. They form temporary dipoles, okay? Make sure, temporary dipoles. What about polar molecules? They always have a dipole, yes? Why do they always have a dipole? Well, because there's always a negative end and a positive end to the molecule, right? Polar, HCl. There's a partial negative, there's a partial positive. We know which one's negative, we know which one's positive. What about in a nonpolar molecule? Is there a difference in electronegativity in a nonpolar molecule altogether? No, right? So we don't have that partial negative and partial positive, but they form them spontaneously, okay? And they do that because electrons are in constant rapid motion, and for a brief moment, there's going to be a distribution that's not quite balanced out, okay? I'm going to show you an example here, and it's a very basic example, but it kind of is true for all nonpolar molecules. When the electrons aren't perfectly distributed between the 2 atoms or between the 4 or the 20 atoms that we have, there's going to be a little bit of a negative end and a little bit of a positive end for a brief fraction of time, okay? That's the temporary dipole. That temporary dipole makes the next molecule kind of look like it, so that there's a temporary attraction there. All right? Or it'll find another molecule that looks like it for a brief fraction of time, and they will be attracted for a very brief amount of time. Now, all these individual ones are pretty weak, but if we have enough of them, they can have a significant effect on molecules. Okay, we call it flickering dipoles. It's like the lights. I'm not going to do it because it freaks people out. But if you turn the lights on and off, that's kind of what's going on with these. If you flick them on and off really quickly, that's what's going on. Okay, it's like a strobe light, basically. They have a temporary negative end, and then they don't. And then maybe this end's temporary negative, and it's not. Okay, and they flip back and forth like this, and they create these temporary dipoles. Okay, it's like a flickering light switch kind of thing. Our example that we're going to do is hydrogen. All right, so let's take a look here. Hydrogen's nice and easy here. We'd have that, and we'd have this, yes? And of course, we're talking about that there, which would be the London force, okay? I picked a really, really simple molecule, okay? But in this case here, how would you know that's a London force? That almost looks like all the other ones. Well, the answer is, well, look, this is 2.2, okay? If we go back to the examples from yesterday, so this pull equals this pull, yes? And this pull equals this pull, right? So we know that that's nonpolar, right? Okay? Those poles are canceling each other out. They're going to share electrons equally. They do share electrons equally. However, electrons are crazy little guys. We never know where they're going to be, right? So, for example, you might say, is that a good? No, this is not really. I didn't show you anything here. You should be like not like, oh, that's hydrogen bonding. You should be saying, hey, where's my diagram for hydrogen bonding, right? Because that doesn't really show you anything. Hydrogen has one proton, okay? And it's got this electron that goes around it, yes? Okay. And again, okay, hydrogen comes in twos, H2, right? Molecular element. We have another hydrogen, one proton. Here, there's the nucleus. And remember, the orbits, remember, they kind of overlap each other, right? So this one has its orbit, and it kind of does this, yes? Okay, and it's got its one electron here as well. I probably didn't draw that the best, but we got these electrons, right? And they're going around and around these atoms. Now, I'm not saying this is exactly what it looks like. I'm just saying you have to kind of take this with, they're just zooming around, right? And in fact, like I said before, they're probably zooming around both of these in like a racetrack, yes? Okay. And at one point, at some point, and you might think this is hokey, but this is what happens. At some point, we're going to get hydrogen here and hydrogen here, okay? Nucleus and nucleus, and let's say these are going around. At some point, we're going to end up with an electron here, perhaps an electron here, okay? Just, I don't know, somewhere there, okay? They're not going to be perfectly one for this one kind of thing. When that happens, electrons are negative, so we get a temporary negative charge, which leaves this as a partial positive charge, okay? And that is able to induce the molecule beside it, which basically means, I'll give you an example of that, but basically make the molecule beside it look the same by pulling on electrons and all that stuff. Or maybe there's another one somewhere in this hydrogen group here, because remember, this is one molecule. We probably have billions of them. So the next one, it's going to find another one somewhere that looks the same as this kind of thing. So I'm going to find perhaps maybe another one that looks like H, okay? And again, that has this 2 electrons maybe over here somewhere like so, okay? And again, we're going to get this partial negative and partial positive, okay? And that's just due to electrons going around. That's what London forces is. Electrons are going around and around, okay? They're going crazy. At some point, they're not going to be balanced out perfectly where they need to be. They're not going to be, they're still sharing them equally, but they're just not balanced out because they're going around all these molecules, all these atoms here. We don't know where they are. So for this, look, partial positive, partial negative, for this brief fraction of time, okay, we're going to get this attraction there, partial positive, partial negative. That is the London force, okay? That is what a London force is. Now, I'll keep going with this, but as we continue with this, you might say, well, okay, how long does that last? Well, as long as the electrons are there. Well, how long is that? Not very long. They're zooming around pretty quick. So now we got a hydrogen that maybe looks like this. Okay, I'm just gonna, is that okay if I just do this now? Maybe the electrons are here and here. Well, guess what? They're split up pretty evenly now again, right? So maybe that is the off part of this light switch. So now there's not a partial negative and a partial positive end anymore. They're nicely split up like they're supposed to be, I guess. And as they continue to zoom around here, now the electrons might even be over here, the two electrons. And again, we'd find another molecule, or we would try to make this molecule look like this one and have the electrons there and there kind of thing. We get a partial negative here and a partial negative here and a partial positive. And again, we have this brief attraction there while these electrons are in that specific spot. We have this brief attraction, which we know as the London force. Okay, and again, they probably go back to neutral at some point. They probably switch again. They switch. They're always on and off, on and off, on and off. Okay. The key here, though, okay, and like I said before, a key word here, they're temporary. Okay. I would say with a dipole-dipole or a hydrogen bonding polar molecule, they're permanent. They're always going to have a negative end and a positive end, right? These are on and off. Okay. Which one do you think out of the three that we've talked about so far, London, dipole-dipole, and hydrogen bonding, if you had to rate them, which one is the strongest? Hydrogen bonding, yes. Which one is the weakest? London, okay. Dipole-dipole is kind of in the middle somewhere, yes? Okay, because London is temporary. It's not even a full positive, full negative end, partial, I should say. It's flickers on and off. Sometimes there's not even a partial negative, partial positive. Okay, so that's what London forces are. Is that okay? Questions, anyone? It just depends on where those electrons are. And like I said, electrons are going super fast. So in the amount of time that we talk about electrons, they've gone around bajillion times and they've flickered on and off a bajillion times, you know. Now again, if you have a lot of molecules, you may have a lot of these temporary forces. And the more temporary forces you have, the better they're going to stick together. Okay? All right. So it's kind of like a balloon. You know, if you ever rubbed a balloon on your head and then stuck it to the board and it sticks there. That's kind of what that's what this inducing thing looks like as well. So if it can't find a molecule that looks like it, it'll kind of say, okay, well, look, I'm a partial positive end. You kind of need to be a partial negative end. So it'll kind of pull the electrons or kind of push them away kind of thing, maybe a little faster, a little slower, whatever the case might be, and try and make that other molecule kind of look like it so it kind of works out a little bit better. Okay. Again, by the time that's happened, it's gone back to neutral. Okay. So we can kind of think of that. You know, the force that holds the balloon to the wall is the electrostatic force between positively charged spot on the balloon and the negative end of the induced dipoles in the wall. The positively charged balloon induces the dipoles to form and then sticks to them. And then, as you know, what happens to the balloon eventually? It falls, right? Because that force wears off, right? Same kind of thing with those. All right. Now, let's just real quick here. As I said before, each of these is pretty weak, right? They don't last for a very long time. They're pretty weak. But if you have a lot of molecules or a lot of other things going on here, we can have a lot of these temporary dipoles, London forces. There's two factors that help with London forces or that affect London forces. So we're going to take a break there. These temporary dipoles, they're pretty weak, but if we have a lot of them, they can have a significant effect on the molecule. Two things affect London forces, and remember now, here's the key. Two things affect London forces, because those are nonpolar, but remember, London forces are in all molecules, right? So this not only affects London forces nonpolar, this would affect dipole-dipole to some degree, and also hydrogen bonding to a degree as well, okay? So there's two things that affect how strong they are. Notice back to this example here. Okay, well, we talked about this, remember? FF is a gas, it's a gas. All of a sudden, BRBR is a liquid. Why is that? Why is II a solid now? These are all London forces. And then we talked about, well, they have electrons that go around. Why is that, though? Why do we get this state change? Obviously, these bromines here are sticking together decently well to make a liquid. These are sticking together really well to make a solid. So why? What is the what's the key here? Why are we going from gas to liquid to a solid here? And that the answer is, well, the first one is actually exactly what we're going to talk about. Oops, where did I go here? Is this, but before you start writing, I need to switch this as I'm going to put here number of electrons. I think is better to. It's true of the molecules increases as the number of electrons of the molecule increases, the attractive force increases due to the number of electrons present. That doesn't really make sense, does it? Let's put it this way. The more electrons you have, the greater the London force. Okay? The more electrons you have, the greater the London force. And I'm going to show you this example. We might want to write down the next part here. So the more electrons you have, the greater the London force will be. Okay. When we talk about London forces, we're interested in the electrons. So actually, let's go back to this diagram right here. So if I look at these, okay, these four examples here, we can add up how many electrons are going around. Look, if you have electrons going around and around, okay, there's going to be chances for distortions, yes? So when I talk about electrons here, let's talk about FF for example. In this molecule right here, this F2 fluorine, right? How many electrons do I have in going around and around this atom? The answer is, well, 2 in the first, and then 7 in the second, yes? So that's a total of 9, yes? And there's 9 and 9, so this is 18 electrons, okay? There's 18 electrons there. So I guess the question is, look, if this is 9 here and 9 here, what are the chances that we're going to get exactly 9 and 9? And I'm going to tell you, probably not that good, right? I mean, you might end up with 8 and 10 at some point, yes? Like as far as the distortion goes. Or maybe even 7 and 11, which we're not going to go to, okay? Okay, not funny, okay? But, you know, you're going to get maybe not a quite equal distribution of these electrons. So, but that's not enough to make it, this attraction here strong, okay? It's still a gas. Here we got what? I believe this goes to 17 and 17, yes? Which is 34 electrons in total, okay? Well, there's going to be more electrons going around and around. What's the chance of it getting exactly 17 and 17? Probably less, okay? Even if it was 16, 18 or 15, 19. Yeah, that could happen, okay? So we're probably going to have more temporary distortions, temporary dipoles here. Again, it's still a gas. Now we get to bromine, which is, I want to say, 35 and 35. Yeah, that's right. 35 and 35. Now we have 70 electrons going around those two atoms. 70. Okay? What are the chances that we're going to get 35 and 35? Less. Okay? In fact, so many less. There is so many temporary dipoles happening with this molecule because of that not equal breakup of these electrons. Okay? Just where they are. There's so many temporary distortions that we now get this into a liquid form. This is now increased enough, this right here has increased enough to hold together good enough to make bromine a liquid. Okay, does that make sense? Questions? And if you do II, captain, my captain, okay, I think it's 53 and 53, which would be 53 and 53, 106. Okay, there's 106 electrons going around 2 atoms. What are the chances that it's exactly 53 and 53? Very not good. Okay, that doesn't make sense, but you know what I'm saying. Not good. There's going to be a lot of temporary distortions. A lot. The chance, because the only way that this is perfectly non-pole, like perfectly shared equally, is 53 and 53. But you could have 54 and 52. Yeah, 52. I haven't done math for a while. That whole March thing really messed me up, last year. 54 and 52. Okay, well, there's a little bit of a distortion there. So right away, temporary negative, temporary positive. Okay, it goes to 50, 56 even. It's like there's tons of options here, right? So you're going to get so many of these temporary dipoles that this is so strong that they're actually locked in together. Okay, and that this molecule is actually locked to this one now. There's so many of those temporary distortions. There's so many of them that they're locked in as a solid. Okay, so the more electrons you have, the better chances of distortions. The better chances of distortions, the stronger the London force. The stronger the London force, the better chance you have from going from gas to liquid to solid. Okay, and that's with all molecules. We're not done. Just wait. Don't just relax. We got 10 minutes. Sure. Close enough. 10, 100 minutes. Now, good? Okay. Does anyone have a question about this? Like, I'm hoping you do, actually. Your Bachek. Hey, come on. Gas, liquid, solid. The question is, come on. Give me all you got. That's a movie. I like that movie. It's one of my favorites. What's the question? Yes. Thank you. Don't you want to know? Come on. That's perfect. That's exactly what I'm looking. How do you know what's the magical number that goes from a gas to a liquid to a solid, right? How many electrons do you need to get it from a gas to a liquid? Because 18 wasn't enough. 34 apparently wasn't enough. 70 is all of a sudden a liquid. How do you know, right? And the answer is no clue. Okay. Don't know. What about a liquid to a solid? What's the magical number? What's the number? Yeah, I don't know. Okay. It depends on what the molecules are. It depends what they look like. There's actually one other factor we need to consider as well, which apparently everyone thinks that we're going to do tomorrow, but I think we're going to start today because you're packing up, so I want to prove a point here. But there's another factor that's involved here too, so we can't just think about size of these electrons. We have to talk about the next thing as well. But the answer is I don't know. There's no, you can't be like, well, it's somewhere between 34 and 70. Not necessarily. Okay, it just depends. So that's one thing to consider there. Okay, size. The next one, like I said, is the shape. So 2 things that you need to know. Here we go. Size and the shape, and these are super important. So don't pack up yet. I better pause